we have two mountain bikers, Stacy and Christina, and they're starting the bike ride at the same time, but at different locations. Stacy starts at point S. So let's draw that. Stacy here, she is at point S. And Christina in blue at point C. Maybe she's over here. And they're in great shape and travel at constant speeds, which makes our life a little bit easier. So we have constant velocities, and they travel at constant speeds throughout the ride. After 20 minutes, they pass each other. Well, where are they heading? What's their route look like? Let's keep reading. Stacy is headed for point C. So she's going right for where Christina started, and maybe that also means that Christina is going to head to where Stacy started. Let's see what they say. She gets there 40 minutes after she passes Christina. So I think they mean Stacy gets there. Misspelling. Sorry about that. T-H-E-R-E. She gets there. Where? Well, she gets to where Christina started 40 minutes after she passed Christina. How many minutes after Stacy arrives at point C will Christina arrive at point S? Okay, so their path is, here it is brown for dirt, right? Basically a straight line from one point to another. Maybe the path is waving. It doesn't really matter because Stacy's heading to where Christina began her bike ride, and Christina's heading to where Stacy began her bike ride. And somewhere along the way, let's put it right here, they're going to pass each other. This is like the meeting point right here. This is where they pass each other. And we're told that, well, they pass each other 20 minutes into the bike ride. And then it takes Stacy another 40 minutes to get where Christina had actually began. And what's so interesting to me is that that's all we need to figure out the answer to this question. It seems like such little information, and it seems like we can't build anything from that, but we can. Keep in mind our key formula here, which is that distance equals a rate times time. And we're going to set rate equal to velocity. We're going to use that language. So velocity is how we're speaking about rate. Okay, well, we don't know much about these two bike riders other than the fact that whatever velocity Stacy's traveling at, who knows how fast she's riding, her velocity after 20 minutes brings us to the passing point. So Stacy's velocity times, so velocity times time, rate times time. So velocity of Stacy times 20 minutes brings us to the passing point. And the same is true for Christina. Whatever her velocity is, we don't know how fast she's going, but that velocity times 20 minutes will bring us to the passing point. And we also know that after Stacy passed Christina, it took her 40 minutes to get here. Well, that means that in this part of the path, the velocity of Stacy times 40 minutes gets us to point C. And already it seems that we're starting to get this nice connection where the velocity of Stacy times 40 minutes equals the velocity of Christina for 20 minutes. So Christina can here cover all this distance in 20 minutes, and Stacy covers it in 40 minutes. So we get some instinct here that Stacy's going a little bit slower than Christina because it's taking her twice the amount of time to go the same amount of distance, and that's going to help us out. So anyway, how many minutes after Stacy arrives at point C will Christina arrive at point S? What can we do? Well, let's write the velocity of Stacy in terms of Christina and see if that helps us. So the velocity of Stacy times 40 equals the velocity of C times 20. What we can say is that the velocity of Stacy equals the velocity of Christina, and then 20 divided by 40. We divide both sides of this equation by 40. That gives us that the velocity of Stacy is equal to 1/2 the velocity of Christina. And that makes sense because Christina is traveling twice as fast. So take Christina's velocity, times it by half, and you get the slower speed, that of Stacy. We know the velocity of Stacy equals 1/2 the velocity of Christina. So we have this piece of information, and that tells us, well, here we have the velocity of Stacy times 20 minutes. That covered this distance right here, and that's what we're looking at. And we're going to plug in our value for Christina into the velocity for Stacy. So that means that velocity of Stacy for 20 minutes, which we knew covered us up to the passing point would equal 1/2 the velocity of Christina times the same 20 minutes. And that means that 20 times a half is 10. So 10 times 10 whatever minutes, or minutes actually, sorry, not whatever. 10 minutes times the velocity of Christina will cover this area right here. So this problem is asking how many minutes after Stacy arrives at point C will Christina arrive at point S? Well, actually, I think I made a mistake when I was writing this problem. And here's what I'm realizing right now. Stacy will arrive at point C after Christina arrives at point S, not the reverse. So it says how many minutes after Stacy arrives at point C, so Christina will arrive at point S before Stacy, because she's the faster rider. So what that means is that we should say how many minutes after Christina arrives at point S will Stacy arrive at point C. That's what it should say. So it's going to take Christina 10 minutes to get from, I'm going to use green now, I'm running out of color here. Take her 10 minutes to get from the passing point to where Stacy began. So that's 10 minutes. But it took Stacy, 40 minutes to get to where Christina began. So it took Stacy 30 minutes more to get to point C. Or we could rephrase the question to say that Christina arrived at point S 30 minutes before Stacy got to point C. Or we can say Stacy got to point C 30 minutes more. It took her 30 minutes more, or 30 minutes after Christina arrived at point S, depending on how you look at it. So this part of the question definitely needs to be changed because Christina is the faster rider in this problem.